because every 4 years we get a new computer, and I'm up for a new computer in August. So they're just going to have me limp along for today, or for months, and then just get me a new computer. Okay, guys. So you may remember that this was a backwards process. That we said there are 3 steps to writing balanced equations, of which step 3 was using coefficients to balance the equation. And guys, that's what's represented here. I gave you the formulas for the reactants and the products, and you not simply, but you balance the equations. What do you need to talk about? Yeah. J? Yeah. So guys, any questions on this screen? These guys? I don't know about you, but on letter D, I finally got frustrated and just had to strong arm that thing. Because there was chlorine here and there, I just could not get this thing to balance. So guys, what I did is I put a 1 there, tried to get it to balance, couldn't get it to balance, erased it, put a 2 there, still couldn't get it to balance, finally put a 3 there, and then I was finally able to get it to balance. So guys, sometimes you just have to do it through trial and error. So you guys are really all okay on this page? Okay, and so you said, Isaac, sorry. On which one? Yeah. Yes. Yes. Okay. Oh my gosh. Just between these. That's brilliant. Wow, that's way more than I could have come up with. That's awesome. Yeah, absolutely. I think they're definitely worked, right? The only problem would have been is if messing around with this somehow changed the aluminums. Then it would have got ugly. But yeah, that's a great idea. So these sort of already balanced, so you just knew you had to deal with these. That was, yeah, nice work. So guys, anything else on this screen? So J, you said, is in Jonathan? J? Okay. All right. So here... and drawing dots, so H-I-J. Okay. Oh yeah, this one's horrendous too. I had to do the same thing, London, that I just described on D. I finally just had to strong arm this thing. So literally, I put a 1 here, and so the idea is, here's what you put a 1 there, and then that's the only thing you can't mess with. So I'm like, okay, so if there's a 1 there, then I've got 1 SI and I've got 2 SIs, and I immediately know that doesn't work because 1 doesn't balance with 2. So I said, all right, so let's try this. So I put a 2 there, and that gives me 2 SIs, and then that gives me 2 SIs. So I'm like, okay, this is starting to work. So then I looked at fluorines, and there's 8 fluorines, and there's 12 fluorines. So, wait a second, sorry. Those have got to be gone as well. So I went, okay, so now I've got 8 fluorines, and here I've got 6 fluorines, and leaving the 2 there, there's no way I can get that to balance. So then I had to start over again, and I went, okay, I'm going to put a 3 there, and I'll pretend like those aren't there. So I went 3 silicones and 1, and so I actually skipped the silicons at first because I'm like, okay, I've got too many, so I can sort those out later. Then I went 12 fluorines and 6 fluorines, so that put a 2 there, which then balanced the silicons, and then the others came together too. So that one I just had to do with just trial and error. So, because... did anyone come up with a better way to do that one? That's all I had. I just had to sort of strong arm it. What else, you guys? Any questions on through K? You're good? Okay. So then, guys, moving on from there, Problem sets 2 and 3 were removing another layer of support from you. So in the first part, I gave you the formulas, you balance the equations. Then starting in set 2 and moving into set 3, you were not given the formulas, so you had to write the formulas for the components and then balance that. With that said, guys, a couple things I want to talk about. Letter A tends to be confusing because you're looking for multiple reactants. But guys, you'll notice that in the question, if you're looking at it, it mentions that this thing was heated. And the idea is that when you heat this thing, it's simply breaking apart. So the hope is that the word heated doesn't mean necessarily one reactant, but when you see that word heated, it tells you that everything before that is the stuff that's being heated, and therefore the reactant, and there was only one. The other that I want to talk to you about just really quickly is this stuff. So guys, please remember when you're balancing equations that we've got these diatomics: iodine, bromine, chlorine, fluorine, oxygen, nitrogen, and hydrogen, and you got to watch out for those. So in those instances, those are diatomics, and make sure that when they're by themselves, you're giving them the 2, which changes the way these things balance. So questions on any of these? Yeah. Yeah. Hold on, let me read with you. So copper combines with sulfur. Yeah, go ahead. Yes. It doesn't matter. And actually, it's not copper 1. We're not going to get into this in this class. But here, copper actually has a charge of 0. And so the rule, and again, you don't need to know this for here, but anytime you've got an atom in its elemental form, like a chunk of copper, by definition, its charge is 0. It has all the electrons that it wants. Protons and electrons are balanced. It has no charge. So that actually has a charge of 0. What happens then is it takes on a charge of +1. And where does the electron go when it goes from 0 to +1? And the answer is the electron goes to sulfur, and sulfur now has a charge of -2, and it actually, this happens twice, and so 2 copper atoms each give up an electron to sulfur in order to make the copper 2 sulfide salt, but it starts actually with a charge of 0. Is that okay? But that said, if they didn't tell you that was copper 1, there'd be no way for you to do that. So, and this is actually another kind of reaction that we don't talk about in here. It's called a redox reaction, but we don't get into it. What else, you guys? Other things you want to talk about? You sure? Both 2 and 3? You're all good? Okay. If you're comfortable, then guys, please, back of hand, hey Siri, whatever you need to do, make a note to yourself to turn this in before midnight tonight. And guys, you just need a sheet of paper, a periodic table, and an ion chart, and we're going to get started. Hello, O'Reilly. Hey, you have not taken the test, correct? You have? Did you take it late? Time before. Okay, I don't have a score for you. We need to talk. Yeah, don't worry about it. I know we're going to go, hey, wait, you have a really big problem, and oh, by the way, let's keep going. And I know that's not fair. We'll figure it out. But yeah, unless I read Skyward wrong and just didn't read horizontally from your name to a 0 in the grade book, we'll figure it out, though. We'll be all right. I promise. All right, so this goes away. So guys, again, periodic tables, ion charts, note-taking materials, and here we go. I think you're going to find this interesting. At least I do. So guys, the topic for your notes today is reaction types. The date today is the 25th. Holy smokes, March is flying by. You guys know this time next week we're going to be sailing into spring break? That makes my heart happy. That's a good thing. Yeah, and did you guys put this together? That we do not have Wednesday school anymore for the rest of the year. What? And I know I shouldn't say it that way because Wednesdays is an online learning day, and certainly it's not a day off. It's just school at home, which for the most part we know isn't true. Yeah, guys, we don't have Wednesday school anymore. Like we don't have, you know how like the last 2 weeks we've had school on Wednesday because we haven't had Monday school? We don't have another broken week for the rest of the year. So we'll have Monday, Tuesday, Thursday, Friday school for the rest of the year. That makes me happy on the inside. All right, so guys, reaction types. The date today is the 25th. And guys, what I want to do before we get started is I want to put all of this in context for you because context helps you learn. So guys, let me put this in context. So guys, this should look familiar to you because this is your notes from last time that you took on the notes page that I gave to you. And guys, let me sort of put this in place for you. So gang, this was part 1 of our homework that we just looked at. Balancing equations by using coefficients. Then guys, this was part 2 of our homework where you wrote the formulas for the reactants and the products and then you balance the equations. Well guys, now, next time just became what we're doing now. So guys, today what we're going to do is we're going to remove another layer of support, and I'm not going to tell you what the reactants and the products are. So you're going, wait, how am I supposed to know what they are if you don't tell me? And the answer is because reactions tend to happen through predictable patterns. And so you are going to learn 5 patterns today. And by knowing these patterns, you're going to be able to predict the reactants and products, then write their formulas, then balance the equations. And then, guys, what you're going to see is most of the reactions that we're going to talk about today, we're going to do in lab on Monday. You guys ready to go? Okay. Now, before we get started, there's a couple things we need to talk about. First of all, don't write this down. But guys, let me set the stage. So here's where we are. So right now, we know that chemical equations represent reactions, and we know how to balance them. Well, guys, today what we're going to do is we're going to talk about 5 general types of reactions. Do not write these down yet. This is our to-do list for today. So guys, these are the 5 reactions that you're going to be introduced to today. Now, let me make this easier for you. Here's what you're going to find. Guys, these, not surprisingly, are almost exactly the same. Single displacement and double displacement reactions are very, very similar. So if you understand one, you will understand both. Then what you're going to find here is that synthesis and decomposition reactions are opposites of each other. And then, guys, combustion just means to burn stuff up. So basically, you only have 3 things to figure out. Single and double displacement are related. These are opposites, and this is fire, and after that, you're good to go. So there's really only 3 things that you need to keep track of. Now, guys, along the way, this is how this is going to work. So let me organize this for you. So, guys, what we're going to do is we're going to do these one at a time. And for each one of these reactions, I'm going to give you the following things. First, I'm going to give you a definition. Then I'm going to give you a general form. Then I'm going to give you what I call a rule of thumb. You're going to find these helpful. And then, guys, we're going to look at an example. So we're going to do these 4 things 5 times, and when we're done, we're done. Groovy? Okay. So with that said, one other introductory thing, and then we're good to go. Write this down. So, guys, subscripts. Scratch this into your notes. This is going to be important on Monday, not today. You can't do this today. But guys, on Monday when we go to lab, you are going to include subscripts in your balanced equations to indicate the phase that these substances exist in. You can't do that today because you're not actually playing with the chemicals, so you don't know if they are a solid, a liquid, or a gas. But guys, those are 3 of the 4 subscripts that you're going to be introduced to. So if you're holding something that's a solid, you'll subscript an S. If you're holding something that is a liquid, you'll subscript an L. If you're looking at something that is, or producing something that's a gas, you'll subscript a G for gas. The only other one that you need to know is AQ, which stands for aqueous, which comes from the Latin term for the same place we get agua or aqua. Guys, aqueous means dissolved in water. So if you've got something that's dissolved in water, you'll subscript it AQ. Again, don't worry about that today. Just wanted to introduce it in prep for Monday. All right. You guys ready to go? 5 reactions, 4 bits of information. Rinse and repeat. When we're done, we're going to work on homework. Y'all caught up? Okay. Guys, single displacement first. In order for you to understand what a single displacement reaction is, guys, you got to understand what displacement means. So that becomes the next thing in your notes, just heading, single displacement. And then, guys, watch really carefully. Watch the pen cup, because if this makes sense to you, you're going to understand what this reaction does. So this is the place, displacement, this is the place where the pen cup belongs. When I do that, that is not displacement. That is moving, but it's not displacement. So guys, what do I have to do in order to displace the pen cup? Go ahead, Sam. Put my coffee cup in its place. Guys, displacement doesn't just mean to lose, it means to put something in its place. Now, if it's single displacement, how many times does this happen? Once. So guys, a single displacement is a single exchanging of partners. So there's your definition. So following the definition, the next thing that I promised you was a general form. So guys, let me give you the general form for this reaction. Scratch this down with me. So guys, we're going to go A plus BC. This is the general form of the reaction. So A is an element and BC is a compound. But now let's remind ourselves, guys, in compounds, BC, which one always comes first? The positive guy or the negative guy? Positive guy, right? Sodium chloride, not chloride sodiumide, right? It's always the positive guy first. So guys, let's do this. Let's say that A is a positive, is a metal. It's a positive ion. So guys, will A hook up with B or with C? C, because A is positive, C is negative because it's second, and so A hooks up with C. What happens to B? Well, it just got displaced, and so B goes home alone. It's very sad. It's like getting low-crawled at a dance. No. And here, let's do this. Guys, now let's reset the stage, and now let's make A a non-metal. If A is a non-metal, then does it hook up with B or C and write the products? And guys, think before you write, because this one's a little different. Now A is negative. So guys, what does A hook up with, B or C? A hooks up with B because B is positive. But guys, talk to me. What's wrong with this? It's the wrong order. Which one goes first? The positive. Good. So the products then, I wonder if I can just delete this. Yeah, one more. So guys, the products then are B, A, and C goes home alone? Yeah. Did I do that right? I think that's right. It's an ugly plus sign, but you get the idea. Yeah? Go ahead, Sam. It is. So here's the idea. Now A is negative. So A snakes in here, hooks up with B, and C goes home alone. No, this isn't a charge. This just means and this. It's like the word and. Is that okay? You guys good? Are we okay? All right. So guys, let me then give you what we call the rule of thumb. So guys, when you're doing reactions and you're like, is this single displacement? Here's the way to know. If you have an element reacting with a compound, that will be single displacement. Now, Jessica, the thing that's interesting is these reactions also tend to be like the one, you're fine, tend to be like the ones that you brought up in homework. It was an element and a compound. They also tend to be redox reactions, but we're not going to talk about that. All right, you guys good? So let's do this. Here's an example. So guys, scratch this down with me big. And you may just be doing this reaction in lab on Monday. Nudge, nudge, wink, wink. All right, guys, so let's tear this apart. We've got zinc. We've got hydrochloric acid. Does the zinc hook up with the hydrogen or the chlorine? What do we need to know? Charges. So we go to our periodic table, and zinc, element number 30, is +2. Hydrogen, element number 1, is +1. Chlorine is -1. So guys, go slow, because there's a lot that's about to happen here. Does the zinc hook up with the hydrogen or the chlorine? Chlorine, but what? If zinc is +2 and chlorine is -1, how many zincs do we need and how many chlorines do we need to make them balance? How many zincs? 1. How many chlorines? 2. Good. So this is ZnCl2. Wait a minute, it doesn't balance. It's not supposed to. Guys, we are writing the formulas correctly first, then we'll balance the equation. If zinc is +2 and chlorine is -1, it's ZnCl2. Then guys, who gets the bootski? Hydrogen. But this is not as sad a story as you might think, because hydrogen just finds a buddy and goes out for drinks. Why did I put the 2 here? Because hydrogen is diatomic. It's one of the 7. Iodine, bromine, chlorine, fluorine, oxygen, nitrogen, hydrogen. Ever by themselves, you huck a 2 onto it. Yep, is that good? Now we need to balance it. So guys, we've got 1 zinc, 1 hydrogen, 2 hydrogens. So we put a 2, 2 chlorines, 2 chlorines, zip, bang, pow, we're out the door. Yeah. Yeah, so this one will always be positive and that one will always be negative. Yep. And London, you're going to see even more of that when we do double displacement. You guys good? Questions on that? Okay. So now, guys, let's do it twice. If single displacement is one exchange of partners, double displacement is a double exchanging of partners. So guys, try this. So now let me give you the general form. So AB plus CD. Predict the products. Given what you know, do you see, London, how what you just asked ties in even more to this? Because I'm going to move this over a little so I have space. So AB plus CD. Can we talk about it? So guys, who does A hook up with, C or D? This is positive, and if it's helpful, you can do this. Positive, negative, positive, negative. So A hooks up with D, positive first is AD. So the A hooks up with the D, then the C hooks up with the B. But guys, which one goes first, the B or the C? The C, because that's positive. So our other product is CB. All right. So guys, let's just pause for a second. So what we've got here is we've got a reaction, think about this, we've got a reaction where we have a double trading of partners. The positive hooks up with the negative, and the positive hooks up with the negative. Sound familiar? Do you see it? What is it? That's how you make precipitates. Guys, that whole lab that we did, remember the thing with the ions and the squirty bottles? And guys, every single one of those reactions that formed a precipitate was a double displacement reaction. I couldn't say it to you then, but guys, think about how we did the lab. We took the positive of one bottle, the negative of the other, the positive of the other, and the negative of the one, and we traded partners. Guys, every single one of those reactions was a double displacement reaction. So, with that said, this then is the rule of thumb. Anytime you have compounds going in and compounds coming out, that will be a double displacement reaction. All right, so let's look at an example. This guy. I used to love to do this reaction for my classes as a demonstration, but I can't anymore because we can't dispose of the lead. It's super toxic. But it's actually really cool, and Isaac's exactly right. It forms a precipitate, but the precipitate is like this gorgeous, vibrant yellow color. It's really pretty. They used to use it as a paint pigment. You've heard of lead-based paint. Yeah. But we can't do it anymore because it kills small children. It's very sad. All right, guys, double displacement reaction. What do we need to know? Charges. So, guys, we find potassium. Potassium has a charge of +1. Oh, I'm going to switch to red. Guys, potassium has a charge of +1, which means iodine's got to be -1. Now, guys, we've got a problem. You look up lead, element number 82. Is it 2 or 4? Isn't it 2 and 4 the choices? Yeah, we don't know which one to use. So what do? Well, we break this in half, and we find nitrate on our polyatomic ion chart, and nitrate is -1. So nitrate is -1 times 2 is -2, so this is +2, so this is +2. We figure out the charge of the lead by working this backwards. Again, a skill that we learned weeks ago. So, guys, let me just clean this up. +1, -1, +2, -1. Okay, so now we need to reorganize these things. So the positive from here hooks up with the negative one from there. But, guys, potassium's +1, nitrate's -1. How many of each do we need? One of each. So our first product is going to be KNO3. And you're going, wait, that doesn't balance. It's not supposed to. We're just writing the formulas. Now, guys, lead is +2. Iodine is -1. So we need one lead. How many iodines? 2. So our other product will be PbI2. All right, now we need to balance it. So 1K, 1K, 1I, 2 iodines. So we need a 2 here, but then that gives us 2 Ks. So we need a 2 there. Then 1 lead, 2 nitrates, 2 nitrates. I believe that balances. Groovy? I heard a voice. Why 2? And so in balancing it, let me see if I can back this out enough to show you. So the idea is this. We have 1 potassium, so that's good. Then we have 1 iodine, and that should have been there. So we have 1 iodine, we have 2 iodines. So that means we need to put a 2 here to balance the iodines, but then that gives us 2 potassiums, so now we need to rebalance the potassiums. Is that okay? Go ahead, McKay. Great question. The answer is actually, let me show you the whole picture. So what does this look like? So this actually looks like the lab that we did, as Isaac pointed out. So this is literally what we've got. When we have a bottle full of Ki solution, we have a bunch of Ks and we have a bunch of Is dissolved in water. When we have a bottle of PbNO3, we've got some PBs, and then we've got twice as many NO3s. But all of these are separated in solution. They're not together. You've got leads, you've got nitrates, but the nitrates aren't clustered together. They're separated. So when these react, this potassium goes, hey, yo, and it hooks onto one nitrate. It can't hook onto two because this is +1 and that's -1. So then what will happen is another potassium will come along and grab the other one. That's why this balances with a 2. But understand, they don't move together because they separate when they dissolve. Is that okay? But for us, the practical bit is don't try to balance the equation. If this is +1 and this is -1, you just need one of each. Then you can come back and make up for the other by balancing. Is that okay? That's a great question. What else, y'all? So can you, in your brain, single and double displacement, cluster those together? Is that okay? All right, so let's do this then. The next two that we're going to talk about are opposites. So synthesis and decomposition. So guys, let me define this for you, and then we're going to play with it. So guys, synthesis is defined as a reaction that only makes a single product. A reaction that only makes a single product. So, what then is the general form of this? Guys, you're going to be able to figure this out pretty quick. So we've got A plus B. And if this is a synthesis reaction, what's the product? AB. They just stick together. Guys, it's literally that straightforward. A and B hooked together, you've got one product. So the general form then is A plus B yields AB. The rule of thumb is a reaction that forms one product. For some of you all, this is going to be the most entertaining thing that's happened to you this school year. Because guys, we're going to do this reaction in lab next time, and it will make you chuckle. It goes like this. Here's our example. Hydrogen and oxygen. We obviously know that the product's going to be water, but let's pretend like we don't. So guys, first of all, and McKay, this was to your thought earlier, you notice that hydrogen and oxygen are both 2s? Because they're each part of this group of 7? Is that okay? Okay. So then guys, how do we know how these come together? Well, we need to know the charges. This is +1, this is -2. So how many of each do we need? Well, 2 hydrogens, 1 oxygen. So guys, we find out then that our product, of course, is water. I know that we knew that, but we can pretend that we didn't just to figure out how to figure that out. Good heavens. But guys, what we need to do now then is we need to balance this thing. So we know that our product is going to be water, so I'm just going to fly that in. So guys, our product is water, but now we need to balance this thing. So we've got 2 hydrogens, 2 hydrogens. We've got 2 oxygens, 1 oxygen. So we need a 2, and then we need a 2. Does that sit okay? You good? Exactly. And then we figure it out later by balancing. But guys, here's the part that's going to make you chuckle. That is not the only product from this reaction. Hey, this is not the only product for the reaction. And guys, please write this down with me. There's another product. That other product is energy. And guys, you're going to find out that this energy comes out in the form of an explosion. So when you do this reaction in lab, we are actually going to cause these little mini explosions. It's really, you're going to want to do it for hours. It's quite entertaining. But guys, this thing explodes. It gives off energy in the form of heat and sound and light. And there's a name for that you need to know. This is what is called exothermic. You probably know that exo, like exoskeleton, means on the outside. But guys, when we have reactions that give off or release energy, these are what are called exothermic reactions. And explosions definitely count. Worth the price of admission, yeah? Oh, absolutely. Yeah, anything, there's lots of, well, not lots, there's many different ways to give off energy, and any of them count, yeah. Absolutely, yeah. So, but actually, the thing that's happening, Isaac, is it's actually not, it's not the water or the metal that's exploding. Actually, what happens is, like, if you take a bucket of water and if you huck a chunk of sodium in there, you know that this blows up, right? But actually what happens is this. The sodium attacks the water. I'm out of space. The sodium attacks the water. And when it does, it actually makes sodium hydroxide, and then hydrogen gas is released. It literally rips the water in half. So you can think of water as H and OH. So the sodium hooks up with the OH, the hydrogen gets kicked out. This hydrogen gas then reacts with the oxygen in the air, forming more water and the explosion. So it's actually the hydrogen gas released by the reaction with sodium that blows up. So I saw a video the other day of a guy that threw sodium in water, but instead of, because it's less dense than water, so it floats. So what he did is he put it in a bag that was water permeable and then tied a lead weight to it and threw it in a bucket of water so it sunk to the bottom so the hydrogen couldn't get away. Oh my gosh, the whole bucket, it was amazing. It went big. It was kind of fun. All right. You guys good on this one? You're good? Okay. So guys, do this with me in your head. Synthesis, one product, right? But do you remember what I mentioned to you at the beginning of class? How is synthesis related to decomposition? They're opposites of each other. So guys, if synthesis has one product, what's decomposition going to be? No, not quite. Flip it over. One reactant, two products, or more, but more than one. So guys, and it makes sense, right? What does decompose mean? To break down. So a decomposition reaction is a reaction that breaks apart one product. Or one reactant, sorry. So guys, why don't you take a swing at writing the balanced equation? Or, sorry, not the balanced equation, the general form. So what's the general form of this going to be? So if our reactant then, our single reactant is AB, what are our products going to be? A plus B. Does that jive for a general form? Is that okay? All right, so guys, what then is the rule of thumb? Well, the rule of thumb is one reactant. If you have a reaction with one reactant, it has to be decomposition. All right. You ready for some animation magic? It's actually not that magic, but. So, guys, an example. Please don't write this down, just watch. So here's an example. Yeah? No. What kind of reaction is in front of you? Synthesis, one product, right? So, guys, this is the reaction that we used as our example of a synthesis reaction. But now, guys, watch this. If we do this, it's now decomposition. Get it? All we have to do is flip it, and now we have one reactant forming two products. But you're like, wait, isn't energy a reactant? Guys, energy is not matter. So energy has to go in to make this happen, but we still only have one reactant. Now, guys, when energy is also a reactant, this has a name, and it's not surprisingly called endothermic, because endo means on the inside. So, guys, now you can scratch it down. Yeah. That is a brilliant question. Let everybody finish writing this down and then let's talk. You're going to find out the answer is no. You guys are good. The thing that's really funny, not funny, Rhett, but that was actually a question on the AP test 4 years ago. The question was, does this represent the boiling of water? A surprising number of AP students got it wrong. See, you could write the AP test. And then you could give me a copy ahead of time, and then my kids could do really well on it. And then I'd go to jail. You guys good? So Rhett's question, which was really insightful, was, is this boiling water? And Rhett, let me draw you a picture. Actually, no. Oh, yeah, I'll draw it on here. So let's talk about it. So we've got water inside a beaker, right? And we put energy underneath this in the form of a Bunsen burner, and then stuff starts flying out the top. But what is coming out the top of a beaker of boiling water? Water, right? So here we are breaking intermolecular forces, and these come off as water molecules. That's not this. So here, what we're doing is actually breaking the bonds between the hydrogens and the oxygens, and then the hydrogens cluster together and the oxygens cluster together, and we're releasing hydrogen and oxygen. Which brings up a really interesting question. So if we add heat to water, it boils, and that is not what we're talking about. So guys, the question is, what kind of energy do we need to add in order to get this to happen? Do any of you know? Guys, the answer is electricity. And I used to do this as a demonstration for my students. And then 3 or 4 years ago, actually it's more like 5 or 6 years ago, a kid named Kyle wanted to be our Science Sterling Scholar, and he wanted to do some independent research. And he borrowed my apparatus. It looks like this. It's called an electrolysis setup. It's like a $300 piece of glassware, and he borrowed it from me and then dropped it. So I can't do this for you anymore. But guys, this is actually what we're talking about. And it has
If we connect an electrolyzer filled with distilled water to a source of direct...
Okay, so guys, let me explain to you how this works. So back here, okay, so here's what we've got. We've got 2 tubes that follow down below, and then they meet, and then they go up this way. So what you do is you pour water in here, and the water fills both of the tubes on the side. So this entire thing gets filled with distilled water. See how they meet down there at the bottom? Then guys, in the bottom, we've got a couple stoppers that have holes in them, and there are actually metal electrodes that stick up through those stoppers.
If we connect an electrolyzer filled with distilled water to a source of direct current, we can observe a...
Now we turn up the voltage and we pass some electricity through the water. That's our source of energy.
slow evolution of gases.
Guys, what you'll see is, can you see them from there, that bubbles start to form? That we've got bubbles over here and we've got bubbles over there. Because those bubbles are the hydrogen and oxygen molecules. We're literally breaking water apart into hydrogen and oxygen. But guys, watch really close. What do you notice about the bubbling on the left compared to the right? Lots more bubbles, right? Why are there lots more bubbles on the left? Because water is H2O. There's literally twice as much gas on the left as there is on the right, because this is H2O. By the way, what does that tell us? Well, guys, hydrogen is positive, which means that this is the negative electrode, because the positive hydrogens attract to the negative side, and they form hydrogen. And then the oxygen's on the other side. And if we let this continue to play without doing that, oh gosh, I just went all the way back to the beginning. What is going on? Oh. This is the problem with not having my second monitor. I can't see what I'm doing. Here we go. Well, there's our music. So guys, you can clearly see this is bubbling more. But now what they do is they climb up the tube. And what you'll notice is this is how much gas we collected on one side. This is the amount of gas on the other side, and it's literally twice as much, proving that water is H2O. Huh? There you go. We got one more to go. Guys, the last one we need to do is combustion. Yes, this means lighting things on fire. Oh yeah. But guys, understand that in chemistry, not all fire equals combustion. So guys, combustion is the burning of a very narrow class of substances called hydrocarbons. So the general form then is this: H sub X, H sub Y. Let me zoom into this for you. Plus our good friend diatomic oxygen. And guys, notice our products, carbon dioxide and water. The water goes away as steam. The carbon dioxide goes up into the air. It's a greenhouse gas, thus the problems that we're having right now. But guys, this is literally where that carbon dioxide comes from, because probably the hydrocarbon you're most familiar with is gasoline. Make that an 8 and that a 18, and you've got gasoline, and you burn it and you get a bunch of carbon dioxide. So guys, this is kind of silly, but I'll give it to you anyway. The rule of thumb is the general form of the reaction. You've got a hydrocarbon, which is carbon and hydrogen together, reacting with oxygen. But guys, here's the important bit. It always forms carbon dioxide and water. Your products are always carbon dioxide and water. Y'all good? Yeah? That's a great question, and the answer is absolutely. So if you have a molecule of octane, that has 8 carbons, which means it's going to make 8 carbon dioxides. If you have a molecule of a substance that has less carbon, you get less carbon dioxide. So you probably know that in Utah we put alcohol, right? We put ethanol in our gasoline. So ethanol is actually, ethanol is actually just 2 carbons bonded together. So when we burn ethanol, it releases less carbon dioxide because it's only got 2 carbons. That's why we do it. Yep, that's a great observation. So guys, let's do one together, and it's this. The very simplest of the hydrocarbons, CH4. You guys remember CH4? I was throwing CH4 molecules around the room several months ago. Do you remember that? Didn't I hit one of you with one of them? Maybe that was a different class. Guys, CH4 is Bunsen burner gas. CH4 is natural gas. CH4 is methane, which is natural gas, because this is the stuff we heat our homes with, most of us. So, CH4 and O2. Hydrocarbon and oxygen. Now, in order to predict the products, what do we need to do? Look up charges, move things around? No. Guys, if you see something like this, you don't have to think, you don't have to balance charges. You just got to write down carbon dioxide and water, and that's it every single time. Those are always your products, and then you balance it. 1 carbon, 4 hydrogens, 2 hydrogens, so we need a 2, and then 1, 2, 3, 4 oxygens, so we need a 2. That's it. Now guys, let me save you some misery. The lab that we're going to do on Monday, the very last question in the conclusions, the answer right now is on the board. I'm going to leave it at that for now, but you may want to make a mental or physical note that the answer to the last conclusion question on the lab is represented on the screen and in your notes right now. So when you get frustrated on the last conclusion question, and you might, guys, make a note somewhere that the last conclusion question on the lab, the answer is right here on the screen. So guys, we're done. Y'all good? Grab your homework. Who needs a copy of the homework packet? Anyone else? Y'all good? Okay, guys, let's do this together. Ready? Grab a pencil. Let's get a bunch of this homework done right now. So, guys, notice this. You see how this says homework assignment 2A? Please turn the page. You'll notice there's a homework assignment 2B. We are not going to turn this in. This is additional practice should you need or want it. The answers are posted on our website, but we are not ever going to formally do 2B. We are only going to formally do 2A. So guys, with that said, ready? Looking at 2A, page 1, all you're going to do is in the spaces, identify these as single, double, decomposition, synthesis, combustion. So guys, number 1, what is it? One reactant, what kind of reaction? Decomposition, put DEC. Number 2, we've got compound, 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 compound. What is that? Double displacement. Number 3, one product. What is that? Synthesis. Number 4, compound, 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 compound. What do you got? Double displacement. Number 5, element, compound, compound, element. What do you got there? Single displacement. Number 6, one reactant. Number 6, one reactant. Decomposition. Number 7, compound, element, element, I sound like a cheerleader. Element, compound. What do you got? Single displacement. Guys, we're going to stop there. You can do the rest, but that's all you're doing. By the way, guys, and this was not on purpose. I'm not trying to be tricky. None of these are combustion. I just forgot to put one. My bad. Okay, then guys, flipping these over on back. Oh my goodness. We're going to do number 1 together. Read along with me. It says this. Write the balanced equation. Indicate the type of reaction on the line. Again, single, double, so on. So guys, number 1. We're going to do this together. Do this with me. Oh. Here we go. So guys, number 1 reads like this. Let's do this together. Let me help you develop a problem-solving strategy. So guys, what we're trying to do is we're trying to write the balanced equation for this reaction. In order to do that, the very first thing we need to do is we've got to figure out what our reactants are. So we got to write their formulas. So aluminum is Al and its charge is +3, right off the periodic table. Sulfate is SO4 and its charge is -2 off the polyatomic ion chart. So when those come together, they meet at 6. So how many aluminums do we need? 2, sulfates 3. So guys, our first reactant then is Al2SO43. Now moving along. Our next reaction or reactant is calcium, which is Ca+2, and phosphate off the polyatomic ion chart is PO4-3. Again, those meet at 6, so we need 3 calciums and 2 phosphates. Writing chemical formulas. Now guys, at this point, you need to hit the pause button. You've got to figure out what kind of reaction this is. So here's the way to do it. Process of elimination. Let's do these in order. Can that be a single displacement reaction? No, because it is not an element plus a compound. Could that be a double displacement reaction? Yeah, two compounds. Could it be synthesis? Yes. There is the possibility that we could ram all these things together. Could this be decomposition? No, because it's got more than one reactant. Could it be combustion? No, we don't have a hydrocarbon plus oxygen. So guys, we now have narrowed it to two. This is either double displacement or synthesis. But guys, which one can we eliminate just based upon being practical? There's no way this is synthesis because we can't put all of these together, which means this has got to be double displacement. So if it's double displacement, we are going to have a double exchanging of partners. So the aluminum is going to hook up with the phosphate, and the calcium is going to hook up with the sulfate. Now guys, notice we've already got their charges. So if aluminum is +3 and phosphate is -3, we need one of each. AlPO4. Then, if calcium is +2 and sulfate is -2, we also need one of each of those, and it's CaSO4. Now guys, at this point we just need to balance it, and unfortunately my arrow is too big. Okay, so to balance it, we've got 2 aluminums, 1 aluminum, so we need a 2. Then we've got, hey, thanks buddy. Then we've got 3 SO4s, and we've got 1 SO4, so we need a 3. And then we've got 3 calciums, 2 PO4s, 2 PO4s, and that balances. Lovely? Okay. So guys, with that said, any questions? Okay, yeah, okay. So compounds are elements bonded together. So an element is literally one of the 107-ish that we know of. It's an individual type of atom. A compound are elements bonded together. So there will be more than one element there. Okay. So guys, we need to come back to something that Ryan said a couple minutes ago that we need to talk about. So when we were talking about decomposition, Ryan mentioned this idea that decomposition might be something where we get 2 products, where something breaks down into 2 products. And guys, that isn't necessarily the case. Decomposition can create more than 2 products. So how are you supposed to know? And the answer is you're not. So guys, you will never be asked to predict the products of decomposition reactions. So what that means is this. Guys, look at question number. Guys, look at question number 3. That is a decomposition reaction. The products are table salt and oxygen. There's no way for you to know that other than me to tell you. So please, in your home, write that down to question number 3. The products are table salt and oxygen. Then guys, number 6. The products are water and sulfur dioxide. Then on number 10, the products are copper metal, water, and oxygen. And then guys, finally this, number 12 is tricky. I'm going to tell you right now it's a single displacement reaction. Not that you guys can't do tricky, but I saw the bucking horse and got all excited. That could have been the University of Wyoming. So guys, there you have it. We now have a little short of 10 minutes. Let's definitely get that first page done, and let's get 2 or 3 of this back page done. And then the rest of this will be homework in preparation for the lab that we're going to do on Monday. Go ahead.
So on those, like on number 6 or
Yeah.
whatever,
Uh-huh.
will we have questions like that all the time?
Heavens no. No. But here's the thing that's interesting, Sam. You will in lab. Because in lab, you'll actually do the decomposition reactions and you will test for the products. So you'll be able to figure out what the products are based on experience. Yep. All right, guys, let me stop recording. Let's get some homework done. Dun, dun, dun.